Let's apply Gauss divergence theorem to evaluate the surface integral f dot n ds, where f is the function given by 2x minus zi plus x square yj minus xz square k. And S is the surface bounded by the plane x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equal to 1. Let us draw those surfaces. X equal to 0, that's a yz plane. And x equal to 1, that's a plane that is parallel to yz plane. Y equal to 0, that's a xz plane. And y equal to 1, that's a plane parallel to xz plane. Lastly, z equal to 0, that's a xy plane. And z equal to 1, that's a plane parallel to xy plane. Observe that these three planes will give us a cube. When they intersect, they will get a cube. Now, if we want to calculate the surface integral f dot n ds, where s is the surface bounded by this plane, then you have to evaluate the surface integral over the surface of the cube. A cube is having 6 different faces. So you have to evaluate this surface integral. You have to evaluate this surface integral 6 times. That's a tedious job. Luckily, we have Gauss divergence theorem. So let's write what exactly Gauss divergence theorem says. By Gauss divergence theorem, so we want to evaluate the surface integral of f dot n ds equal to volume integral of divergence of f dv. Now we are given f, so let's find divergence of f. Luckily, Gauss theorem will make our work much easier. So divergence of f is given by del x of I component of f plus del y of j component of f plus del z of k component of f. I component of f, you can see it, equal to 2x minus z. So del x of I component of f, del x of 2x minus z, del y of j component of f is x square into y. So del y of x square into y plus del z of k component of f minus xz square, del z of minus x into z square. Let's compute it. Del x of 2x is just 2, but x and z but when we partially differentiate with respect to x, we regard z to be a constant. So del x of a constant is 0. Del y of y is 1. Del y of y is 1. X square, we regard it as a constant, so we just write it. Del z of z square is 2z, and x is regarded as constant, so x into 2z. So divergence of f is exactly equal to 2 plus x square minus 2xz. Now Gauss divergence theorem says surface integral of f dot n ds equal to volume integral of divergence of f. We have computed divergence of f, volume integral, let's see it. Let's write it. Volume integral of divergence of f dv, we have to exactly cover that cube. We have to exactly cover the volume of the cube. As we said earlier, x is changing from x equal to 0 to x equal to 1. What about y? Y is changing from y equal to 0 to y equal to 1. Lastly, z. Z is changing from z equal to 0 to z equal to 1. Divergence of f, we have computed it. That's equal to 2 plus x square minus 2xz. Now dz, so we will integrate with respect to z first, and then dy, and lastly dx. Now when we are computing volume integral, we will regard, as we did in partial derivative, when we are computing volume integral, so x is regarded to be a constant. So let us determine this volume integral. We will integrate with respect to z first. Integral of z is z square by 2. Rest of the expression we copy as it is. 2 plus x square. 2 plus x square. If you are integrating with respect to z, that's we regard it to be a constant. So integral of 2 plus x square with respect to z is just z. Minus 2x, once again it's just a constant, and integral of z is z square by 2. Now z is changing from 0 to 1. Rest of the expression we copy as it is. X is changing from 0 to 1, y is changing from 0 to 1. We have integrated with respect to x, and we are supposed to integrate with respect to y and x as well. Now let's put the value of y. X equal to 0 to 1, y changing from 0 to 1, no change, we copy as it is. When I write z equal to 0, everything vanishes. When I write z equal to 1, I'll get 1 here, 2 gets cancelled, and minus 1 square. Rest of the expression we copy as it is. 2 plus x square into 1 minus 2 gets cancelled, and so x. dy dx as it is. So we have integrated with respect to z. Let's do with respect to y. Oh, there is no quantity that involves y. We regard x to be a constant. So this is simply equal to 2 plus x square minus x. Integral of constant is just y. Again, y is changing from 0 to 1. Lastly, we have to integrate with respect to x. So when we write upper limit y equal to 1, I'll get 1. When I write upper limit y equal to 0, I'll get 0. So this quantity is simply equal to 2 plus x square minus x dx. We have just to evaluate the integral with respect to x, and that's equal to integral of 2 with respect to x is 2x, integral of x square with respect to x is x cubed by 3, integral of 1 is x square by 2 from 0 to 1. And this is equal to 2 plus 1 by 3 minus 1 by 2. equal to 11 by 6. So we have calculated volume integral using Gauss divergence theorem. So lastly we write, therefore surface integral of f dot n ds equal to volume integral of divergence of f dv, and that turns out to be 11 by 6, and we are done.